Good morning, everyone. Welcome to the Easy Power Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here at Easy Power. And today we're on the second installment of a four-part series we call Introduction to Protective Device Coordination. And the focus for today is on fuses. And as you might imagine, the topic itself is extensive enough that we could spend 4 hours just on fuses themselves and their application. This is primarily an introduction to the topic, so it won't necessarily be an in-depth study on any particular feature. Last week we covered primarily TCC curves, how they represent the milestones or the keystones in the performance of individual devices, and how important data entry is in an Easy Power file to properly represent the performance of the equipment on the TCC curves. We're going to try to do the same thing on fuses today, so bear with us. And as we are in the habit of doing, we'd like to start off with a couple poll questions. We would appreciate your feedback. There's no liability or obligation. The first question is, which type of protective devices do you most often use? So if you would please respond in your particular case. And we were not going to spend a lot of time on the poll questions. We will have a brief quiz at the end of the session to see how things have been received, so we appreciate your participation. All right, looks like we have close to a quorum. Let's call it. Hear how folks have weighed in. It looks like fuses aren't that popular with today's group. Very good. And then the second question is, when using fuses, which part of the solution causes you the most problems? This kind of foretells where we're going to be talking today. So again, just some basic perspective on where you're coming at the topic for today in your particular case is what we're looking for. The other thing that we're trying to focus on is how to utilize Easy Power tools to extract or demonstrate what part of the operation or performance that you're trying to show or you need for your analysis. And again, you're welcome to ask questions at any time. May or may not be able to get to them online, but we will follow up with an email, Q&A email after the session. So it looks like coordination is the primary concern for folks using fuses, so let's kind of get to it. All right, so today's agenda, we're going to talk a little bit about series rating, what that means, and how it's affected, how it's different, frankly, in fuses versus breakers, and then get into the topic of series coordination, and then spend a little bit of time drilling into the NEC guidance regarding fuses and the application of current limiting fuses and higher current applications, and specifically the arc energy reduction options under certain conditions of that fuse size. So something to look forward to. Okay, as we kind of mentioned last week, protection against equipment damage is the primary reason we use protective devices. And so the intent is to minimize equipment damage, reduce the potential for a catastrophic failure, in some cases reduce the risk for people by reducing arc flash incident energy. Often there are legal requirements as required by the code, and then some facilities, there are insurance requirements that they have certain criteria for their protection. Now, when we talk about coordination, it's slightly different in that the purpose is to increase the reliability of the system by making sure we isolate a remote fault as close to the faulting piece of equipment as we can to avoid taking down unnecessarily larger sections of the plant. And Anytime we talk about coordination versus mitigation, there's always a balancing act because they're directly conflicting as far as their initial or individual focus. So the protection engineer must strike a reasonable balance between the two. And that's some of the focus of the new regulations in the NEC that we'll be talking about in a few minutes. Now, clearly, fuses versus breakers, there's some trade-offs that should be considered in terms of the initial design and can be considered when we're talking about upgrading a plant or dealing with mitigation issues. So generally, fuses are lower cost because they don't have, if you will, the intelligence or the capabilities built into them. They do have the ability to be high interrupt rating and current limiting. And by definition, that means they can clear an arc or a fault within the first half cycle of the faulting current. Now, we'll get into the details of that as we start talking about some parts, but it's not just a blanket coverage. The current limiting feature of any individual fuse is limited to a certain range of fault current compared to its normal operations. And when it's in the current limiting range, you do have the coverage of the half cycle clearance. They do have the downside of being a one-time device. In other words, you have to replace it after a fault has necessitated the clearance or using the fuse capabilities to clear the fault. And as such, spares are required. The potential for arc flash reduction is a positive, and with the downside of a potential for single phasing if only one phase, the fuse in one phase clears first. The risk of replacing with the wrong fuse is real, and frequently that can make the difference as far as the changes in a system between one study or one arc flash study and the next update. If for some reason someone has, in the process of trying to keep a plant up and running, replaced a fuse with just what was available and then didn't go back and understand what the impact either on equipment duty or on the arc flash results would be using a different size fuse. There's also the potential or the need to, if we do have a single phase clearance, that, or anytime we have a fault, that we replace all three fuses in a three-phase system because, and we'll see this as we get into the TCC curves, if a fuse doesn't properly clear on a fault, it could be damaged to the point that it's not a repeatable function as far as its ability to clear a fault in the future. So that can be a pro or a con depending upon which way you look at it. Now, is determined by or stipulated in the National Electrical Code, equipment intended to interrupt current at fault levels shall have an interrupt rating at a nominal circuit voltage at least equal to the current that's available at the line terminals of the equipment. And this is the test that's in Easy Power that's utilized to determine this is called equipment duty. And the fuses generally have an extremely high interrupt rating if they're selected properly, and several fuse types can be accepted in a tested series combination. We're going to show an example here, but it is possible to basically upgrade the short circuit withstand of a panel or a downstream system with a higher capable upstream fuse as long as it's properly selected vis-a-vis the downstream equipment. So interrupt rating, there's basically two terms. Fully rated means that each each fuse in the system or each overcurrent protective device is rated, fully rated, for the amount of short circuit current and a worst case fault. So in the case of this one line that we're showing here, we have a maximum potential short circuit available current of 31,400 amps in a 480 volt system. We're using both upstream and downstream devices that are rated for 65,000 amps. So this is regarded as a fully rated system, and it doesn't matter where the fault occurs. The equipment's capable of operating to a manufacturer specification. Now, in Easy Power, this is the default mode as far as evaluating equipment duty. With certain, and this is someplace you want to refer to the manufacturer's directions. In some cases where series rated is required or called for, the ability to enhance downstream limitations. In this case, we have breakers that are rated for 10,000 amps. By using a 65,000 amp upstream fuse or protective device, we have the ability to cover or have an equivalent rating of 31,400 amps for the whole system. But this requires tested pairs by the manufacturer. So both devices will likely clear on the available fault current. The rating for the system is not 65,000 amps. It is basically whatever the combination has been tested to. Easy Power doesn't provide the ratings for series ratings for fuses, but it does for breakers if we have breakers in both locations. We're going to talk about, and all this is in the device library. We'll refer to that in a few minutes. Now, frequently on commercial projects where you have a need to be price competitive, this would be a way to enhance the downstream rating. But again, it needs to be pairs that have been tested by the manufacturer and the published results documented or referred to when we document our one-line diagram. Now, as I mentioned earlier, and we talked about last week, series coordination or selective coordination, the intent is to have the protective device nearest to the remote fault to clear first, although the fault current itself will be felt by at least, in this case, 2 other devices. Common types of fuses include non-current limiting fuses and current limiting fuses. And as I mentioned, not all fuses or not all current will cause a current limiting fuse to quote unquote current limit. And that is clear the arc or clear the fault in the first half cycle. And the only way you can do this is by using or verify this is either use the manufacturer's data sheet or look at the TCC curves. Typically, especially in low voltage fuse curves, they will show a minimum melt curve and or a max clearing time, and that gives us a band of, if you will, interpretation of the actuating clearing process, where and different manufacturers do have a different way of posting the data. And we're going to look at the device library so you can see for yourself how that's represented. When I'm in Easy Power, I have the ability to look at the device library virtually any time I'm in a project. So we're going to open the device library. It's always in the Easy Power folder, device library. The usual designation is standardlib.mdb. And when we're looking at low voltage fuses, AC, you can see we have a host of manufacturers. Let's just look at a couple of them to illustrate my point. So we're looking at the Bussmann catalog, standard bus types, and here are a number of different standard parts, all are rated, or most are rated at 200,000 amps withstand. If we pick out a single type and look at the TCC plot, you can see in this case we're showing both the minimum melt and the total clearing time. So this would produce a band that would give us an indication of the trip setting. And then that will vary based upon the size of fuse that we've selected. And so again, the purpose of using the TCC curve is in short circuit analysis, we will predict the worst case current, and then based upon where the current falls on the horizontal axis, we would plot the clearing time to be the total clearing, the intersection of the short circuit current with the green plot, the green curve, and that will give us the clearing time for that particular fault. That's pretty straightforward. And again, this in and of itself doesn't show us the half cycle clearing time of the current limiting capabilities. But a note to be made is that half cycle is much less than 10 milliseconds. So the current limiting effect is going to be down here, actually below the plot. And so that'll give us a clue as to how much current it takes to be in the current limiting range. A couple other things to point out is, I've had questions come in about how do you deal with cable limiters. Cable limiters, which can be used to increase or enhance the rating of downstream equipment, can be treated just like any other fuse. And so in the case of a 250 current limiting, of course, it's not. So what we're showing here is a total clearing time, and then that would give us the performance of a cable limiter in our system. I want to check another couple manufacturers just to show that everyone seems to have a different perspective. So if we look at Cutler Hammer, we can see that they're primarily using total clearance. They don't talk about a minimum clearance. And so if the recommendation from the manufacturer is to use a 5% or 10% differential, we'd show that plot. If they don't, we'd only show the total clearing time. Okay, that seems pretty self-evident. That's the device library, and it's worth stating, if you find a data sheet that for some reason is not in the device library, contact tech support, and they can make sure that that part that you're trying to use is profiled and included in your model. Now, in terms of coordination, the general rule of thumb is in the same family, as long as you stay with a 2-to-1 ratio, the size will coordinate without, I shouldn't say without fail, but fairly easily. And so I wanted to kind of show that. Let's close our device library. Let's look at, this will do. So here we have fuses used for protection, starting with the 600 amp, a 300 amp, and 150 amp. And the manufacturers stipulate that with that ratio, we should be able to coordinate. So if we go to coordination, I think I've already plotted these. Let's look at the busman comparison. And so looks like we're really close on utilizing this protection scheme for the motor in question. But the 300 amp, the 600 amp curve, and the 150 amp curve are all parallel and won't intersect at least over this current range. So that indicates we have coordination virtually for the whole extent of our fault current. If we look at another one, let's look at another plot. Hammer, same thing. Here we have a 1600 amp and an 800 amp, and you can see they stay parallel. Now, easy power, if there are other values in that family in the device library, easy power will allow me to left click and drag. But that reduced clearance, while it looks like they should coordinate, it's not a guarantee by the manufacturer. So that's, again, left up to you if you have a specific restriction as far as the size of the fuses, being able to tell what the fault current is and how closely you have coordination between different fuses is left to your good judgment. And you'd want to document if you use something other and the justification for using something other than the manufacturer recommendation. And then finally, we're going to look at the gold Shamet. And it's the same thing where we have a 2-to-1 ratio between a 200 amp fuse and a 400 amp fuse. Now, so the issue becomes if we have, if we're using fuses for transformer protection, in the primary, we have to be aware of the need to not be sensitive or not necessarily have the fuse rated such that, especially if it's in current limiting, it could have the potential of interrupting the normal inrush current for the transformer. So in primary protection, the fuse must be up and to the right as far as its TCC curve, assuming a inrush plot of 1/10 of a second. That's 8 to 10 times the full load current for the transformer. And this is usually based on self-cooled rating. So easy power handles the math as long as I keep a clearance between my primary protective devices and the plot of the inrush data point. Okay, so this is from a manufacturer's data sheet, which shows the recommended ratio if we change families. So in a normal family, if we stay within that range, the recommendation for coordination is a 2-to-1 ratio between upstream and downstream. However, if we're going to change family in the process, there's maybe a different recommendation, and that's what this is all about. If we move from an RK1 to an RK5, we'd have to use a different ratio between the upstream and the downstream comparisons. Again, I refer you to the manufacturer's tables for this. It's not something that's going to be handled automatically by easy power. Now, and this is basically showing the same thing, is that we can, I think I already talked about this. Now, the National Electrical Code has recommended settings for transformer overcurrent protection involving breakers and fuses and supervised and unsupervised, or any transformer. The significance here is they give us a number, especially for fuse protection. This doesn't mean I have to set it for 300% of full load current. It means I can set it as high as 300%. And for supervised, as high as 250%. So I wouldn't necessarily go right there. It depends on how much room I need for coordinating downstream devices. But these are the recommendations for primary protection and then secondary protection compared to the rating of the transformer itself. We'll get into more of this in the fourth week, where we'll actually do more specific circuits using fuses, breakers, and relays. Okay, there's been some confusion regarding selective coordination for critical equipment or emergency systems. And so as extract from the National Electrical Code, these are the articles that are affected by coordination requirements. And what they've done is they've added this note and this image to each of those articles, talking about the need to coordinate when we're on emergency energy source versus a normal source. What it boils down to is that the downstream protective devices have to be coordinated. If I go to the emergency source, D has to be coordinated with C, C has to be coordinated with F, and F has to be coordinated with E. When I'm on normal energy or normal supply, I still have to have D coordinated with C and C coordinated with B and C coordinated with A, but A and B don't necessarily have to coordinate. Now, first blush, this is kind of confusing, but what it amounts to is that the restrictive coordination requirement is when we're on the emergency source. It's possible under normal source to have these ratings be the same, and so if I coordinate with one, I automatically coordinate with the other. But the need to coordinate A and B don't necessarily pertain to the requirements in the National Electrical Code for these articles. So supposedly this answers the debate concerning how to handle overcurrent protection coordination on the normal side of the transfer switch. There was a significant discussion on the release started in 2017 of Article 240.67 applying to fuses rated at 12,000 amps or higher, and there was a requirement that became effective January 1st. And so this was promulgated back in 2017 to give people time to come up with the solutions, industry time. And so it's necessary when we do have a fuse protection rated at 1200 amps or higher to document a method to reduce the clearing time anytime the arcing current doesn't clear the fault in 70 milliseconds or less. And so there's a requirement to document what that protection scheme is in that case, and then to have performance testing to show or prove that we've mitigated the process. Now, what's interesting is they tell us what we need to do, but they don't tell us how or what limitations we should set when we're using this alternative scheme. And the alternative scheme includes maintenance mode, differential relaying, zone selective interlocking, or alternative systems. And again, this only applies to fuses rated 1200 amps or greater with a longer clearing time, longer than 70 milliseconds. And again, clearly, it's necessary to use the TCC curves when this is the case. So let's go to this example in Easy Power, because I like the scheme here that we use. Now, the point for making that comment is I have one line that has several different utilities with different properties tied together, and because Easy Power will only allow a single utility source, I can't have individual utilities in my one line. I've attached each with a virtual bus bar or busway, and then have the open switch so they're not necessarily in the circuit. So this gives me the ability to have individual short circuits from different utilities, and we have ratings for 1200, 1500, 2000, and greater. And if we go to arrange for arc flash to see what the results are, we see the clearing time ranges from 89 milliseconds to 70 milliseconds, 69, 117, and 103. So except for the 27 amp, this 27 kiloamp, the two that clear at 70 milliseconds or less, I don't need to do any mitigation, any additional mitigation. I have to do something about these outliers. So I have a clearance on the 1200 amp of 89 milliseconds and clearance on the 61 kiloamp at 117 and 103. So then that takes us to what's the recommended requirement. Well, we would just document in the case of where we have the clearing less than 70 milliseconds or less, we didn't take any further action. We document it, and it's only on these three outlier ones that I have a problem. Article 240.67 specifies the methods available, but it doesn't specify exactly how to set them up. And so those methods include, as I just mentioned, differential relaying, maintenance mode, arc flash, effective arc flash mitigation, current limiting, actuated fuses, or other approved equivalent means. So we're just going to touch on these because we're running short of time. But differential relaying, basically I have the ability to have a relay that senses whether I have a differential current that indicates a fault, and then switches the main fuse or even a branch fuse to trip faster than it would in the normal operations. Energy reducing maintenance switch does the same thing, except we have a switch that we can set to put the relay in the system, and when the relay detects a fault, it trips on a faster fuse. Consequently, it's referred to as a fuse switch or a switched fuse. There's new equipment involved in the marketplace that incorporates ground fault, overcurrent, maintenance mode, and in some cases, zone selective interlocking. These come from a multiple of suppliers. I've got a couple examples here. Here's I think this is from Merson. They have a medium voltage controllable fuse where this solves the problem of having high incident energy when we don't have a downstream main breaker in a medium voltage system. And so the intent is to put a fuse that's switchable on the primary side and then detect fault currents down here and pick a faster trip unit or a faster fuse if we detect a fault. Likewise, the Eaton solution is the thing we were talking about earlier, which gives me the ability to handle multiple types of faults, including ground fault and maintenance mode with varying granularity. And EasyPower simulates this with what's called a fused group, and you can plot the trip curves for the normal fuse and then actuate the relay and show performance on the faster fuse. And in essence, in normal operations, the high current or the normal current flows through what's referred to as the main fuse and the switch. And upon the relay activating on a fault, it opens the switch and forces the current through the quicker acting fuse and quenches the arc even quicker. Then the energy reducing active arc flash mitigations, the ones that I've seen are referred to as quenching systems, which are active grounding. They have some trade-offs. They operate very fast and are apparently basically they convert an arc to a bolted fault, and the system's designed to protect itself against that. And consequently, it can shut down quicker and contain the arc much more efficiently. It's got its own trade-offs because you're going to have to replace some parts once the system's activated, but it's very effective as far as protecting downstream equipment and personnel. Okay, so that's kind of what I wanted to cover. What I'm looking for is system coordinations with fuses can be economical, but there's drawbacks and restrictions. Transformer protection is critical, and it's a good application for fuses. As we indicated last time, proper documentation is important. And before I let you go, if you would please help me out with a couple more poll questions. So, fuses are often preferred over breakers because, and again, this is just to see if I was clear in the presentation. So let's leave this another 5 seconds. All right, looks like we got close to a quorum. Generally, they are lower cost, and they do have their drawbacks. Second question, if fault current is in the current limiting range, a current limiting fuse will, and so if you would please respond accordingly. I'm got my spelling corrected. Sorry about that. All right, got a quorum here. Thank you. Looks like we've got a majority. I paid attention. And then finally, NFPA 70E requires alternative methods to reduce energy if the main fuse, wait for it, and so we got another 10 seconds for this one, and it looks like we got a quorum. So this is a little bit of a trick question. Turns out it doesn't have to be current limiting. It does have to clear within 70 milliseconds. So the real restriction is if we have a 1200 amp fuse that doesn't clear in 70 milliseconds, then we need to have an alternative type of mitigation. Anyway, I'm maybe too clever for my own good. Thank you for participating. All right, well, we kind of run out of time. Look forward to talking to you next week. Please, we have updated tutorials. We have new regional training posted on the website. And if you got other questions on Easy Power tools, by all means, contact tech support at easypower.com. Have a good day.